Okay, multi-objective optimization, whatever. Long story short, all this is, let me make sure it's recording. Okay, yes, it is. Wait, yes, it is. All this is sometimes, you've got a problem where you're looking for one thing. You're minimizing the Euclidean distance. Great. But sometimes you have a problem where you might have multiple things you want to do. And a really simple example of this is in genetic programming, it's not that rare to see someone, their fitness function, like symbolic regression, I want to minimize that. But another thing that they'll sometimes want to minimize is the number of nodes in the tree. Because all things being equal, if I have two functions that get me the same result, but this one uses less nodes, if it's a smaller tree, I like that. Because it'll help eliminate bloat, it'll be also a little easier to understand and everything. Maybe that'll be bad. Maybe some of the bloat's good because it has like vestigial parts to it that might come up later, who knows. But a lot of people do like to have a secondary objective that they just basically minimize either the depth of the tree or the number of the nodes in the tree. So it's multi-objective. We can have as many objectives as we want. But then this begs the question, well, how do I manage these multiple objectives, right? How do I know which one's truly better than the other? And we'll talk about a couple examples to put this question into place. Okay. MOPS, multi-objective problems. So far the most part we're doing looking single, what is the problem, multiple things to optimize. Solution goodness is relative to probably, like sometimes conflicting things. Sometimes you want to minimize this, and while minimizing it, the other objective also improves. But sometimes when minimizing something, you have this conflict where you minimize this, but this gets worse. Like the teddy bear factory with worker deaths. We get better output, but more people die. So we kind of got to find a middle ground there, I guess. So buying a house, number of rooms, style, commuting distance, public transit, surroundings, price. These are very subjective. Who here currently rents a place in town? Who here had any of these things on their list of things to consider? None of those things? This past year is an example. This past year, if you found a place to live, you're winning. I get it. But let's pretend it's any other year. Would you consider the number of rooms there are? Would you consider the style? Well, maybe not so much right now. How long it would take you to get to work? Access to public transit? You're laughing in any Ganesh. There's totally a bus, right? It drives up and down Hawthorne once a week or something. I don't know.
You're missing an important one.
Which one?
How good is the internet?
How good is the internet? That is a good one. And that one's hard to know beforehand.
Especially with like COVID now, or even like before with online.
Yeah. So surroundings, is it in a nice area, and how much it costs. These are all different things. Did you have a question? Or you were just saying, yeah, I care about cost. Me too.
I care about it.
So those are things we care about. But the problem is, when you're looking at a bunch of different potential options, again, not this last year, because you were lucky if you got one, you have these things to weigh. This is a multi-objective problem. It's just, you as a human, you don't really think of these things, like you don't break it down as a mathematical model of, well, I care about this as much as, you just kind of think about it. But in reality, if you're thinking like a computer scientist, we break everything down into the simple steps. What does it actually mean? Well, we've got a whole bunch of things we actually care about. But at what point does the commuting distance and price, where's that like tipping point? You know? There you go, cost and speed. Apparently we've got every vehicle between that car and this go-kart. Here, we do have conflicting things, right? As I want to get a fast car, but I don't want to pay a lot of money. Well, I'm in trouble, right? Because, if I want a faster car, in general, I got to pay a little bit more money. So based on this, I've got decisions to make. So the cool thing, though, is if you look at this, sometimes you'll notice that there is a boundary where we might call this a dominating boundary or a dominating set or something, where, okay, look. All the points under there have a point that's just better than it in terms of both metrics. But on that boundary, we have a decision to make. See what I mean? Like if you take this one, for example, cost. Okay, the cost is like, mid-range, but it's slow. Where this one costs a little bit less, but it's more. This one costs a little bit more, but it's way faster. But like up here, we've got one that costs roughly the same, but it's just so much faster. So anything down here, I don't really care about as much. I care about these ones because this is now really where I've got hard decisions to make. Because now we have the trade-off, where with any of these, there's like an alternative that still like beats it. Where here it's, well, sure, this one beats it in one metric, cost, but it's slower. This one's, So do we see the idea of this like dominating set? How that group up there, like they don't beat each other. The easiest way, scalarization, which is a fancy way, a weighted sum. The easiest way to deal with multi-objective problems is a weighted sum. On one hand, it's really easy to implement. On the other hand, it's really hard to get right. So a weighted sum is, I've got some objective metric, cost. I have some arbitrary number of objective metrics, a 1, a 2, a 3, whatever. Let's say I just have two, objective 1 and objective 2. If I have objective 1 being cost and objective 2 being speed, if I just add those values together and say, like, well, cool, I'll just sum them together, then I'll pick whichever one's best. But the trouble with that is the values don't necessarily easily translate to anything that makes sense. Does this work? I hope I didn't lose all my markers. I think I lost all my markers. No, where did I leave them? I didn't lose them, don't worry. If I have like, well, this one costs $60,000, and I don't know, for speed, maybe I do something silly like 0 to 60. And this one can do 0 to 60 in 10 seconds. Well, then it's $60,010. Where maybe another one costs $61,000, but can do this in 9 seconds. Well, I mean, these numbers are so out of whack that, like, the cost is going to dominate so much of the fitness function that it's kind of silly to just add these together. So what we could do is decide, well, okay, first of all, I want to have these numbers somehow in the same range. And you could do any normalization technique. Take the highest value from each to divide everything by the highest value from each, and you get a value between 0 and 1. Great. Does that make sense? Just scale it. Just scale it down so both values are between 0 and 1. Great. Now they're on the same level. Great. So that solves one problem of having these values way out of whack and them not really making sense when you add them together. The other thing that we might care about is like, okay, look, I care about cost and I care about speed, but I care about cost more than I care about speed. So maybe what I'll do is I will take a weight and put it in front of my cost measure, objective measure, and make it worth like 1.1. Like I care about it 10% more than I care about speed. I mean, it gives me a way to quantify how much I care more about one thing over another. But at the same time, I don't know, when you were looking for a place to rent, did you like come to a precise number of like, I care about price 6% more than I care about location, and 12% more than I care about the amenities nearby, whatever, right? Like, good luck doing that. So one, it's very simple to do. Normalize the values and add a weight in front of it to scale the values up accordingly based on which ones you care about more. The issue, though, is how do you find the numbers for the weights that are really good? In general, it's so easy to implement this in your fitness functions. If you don't realize it now, you will if you ever try. It's trivial. You just take the two things you're optimizing and then add a weight in front of it. In fact, in Deep, it makes it so easy that when you like define the language with multiple objectives as the output, you know how like if you're minimizing, you had to say like -1, right? If you had two objectives you wanted to minimize, you would do like -1, -1. But if you cared about the second objective more, you can do -1, -2. And suddenly that one's more like meaningful. So it's very easy, Deep. But again, what are those weights? Sometimes they're easy to figure out. Sometimes it's too fuzzy to come up with a hard number, right? So how am I going to do that? Yeah, whatever. It can be hard to quantify, yeah. So then there's this idea of dominance. And you know what? I think I have some notes on these slides, and I want to have a look. Can I view the notes? I'm not used to LibreOffice's stuff. Anyone see anything about notes? View? Notes. Okay, there are none. Okay, let's not worry about the notes. Slide. Normal? Okay. So there's this idea of dominance. And this is what we talked about a moment ago when we talked about that car example. So optimization task. Minimize both F1 and F2. And we've got a bunch of things there. And if I look at A is better than B. There's no ifs, ands, or buts about it. If I'm minimizing both things, A beats B no matter what. Do you agree? It's got a better cost and it's got two good small values that beat B. But A is also better than C in that, sure, it matches on one of the metrics, but if you consider, okay, all things being equal, the other objective is the tiebreaker. Do you agree? So sure, they're equal, but because that one is minimizing the other feature more, if I had to pick one of the two, I'll pick the one that's got the smallest as opposed to tied smallest and bigger value. A is absolutely worse than E though. Do you agree? But A and D are kind of comparable. Or maybe comparable is not the right word here. We're in a bit of a pickle. Because, all right, well, on F1, A is better. But on F2, D is better. The question now comes, I've got this conflict. One's better in one metric than the other. How do I pick? What do I do? How do I decide? This is where we run into a bit of a pickle, where it's like, well, okay, it depends, doesn't it? Which one do you pick? Well, which metric do you care more about? And does its value when weighting like mentally how much you care about something? Does one kind of tip the scale on the other? You know, like how do I decide? Realistically, if you're looking for houses and you're looking for something that's cheap and close to the university, if you find a place that's 5 kilometers away that costs $650 a month, or something that's similarly nice that's 2 kilometers away and $600 a month, which one do you pick? The second one, because it's both cheaper and closer. Fantastic. You can ignore the other ones. But if I told you there's something 2 kilometers away that's $700 a month, and something 3 kilometers away that's $650 a month, now you've got a decision to make. Now you're like, okay, well, $50 closer, $50 closer. I have a conflict. I have to decide which one I want. Where in the other case, the one was on all metrics worse than the other, so I'm ignoring it. I don't need to consider it in my decision making. So if I had 10 things I was looking at, 10 rental units I was looking at, some of them are going to be just absolutely worse than the others. But some, you have this give and take. It's better here, but worse there. But that one, well, it's like that, and that one, you've got to decide. So the words we would use is X is better than Y in at least one objective. Okay, wait, solution X dominates solution Y if X is better than Y in at least one objective and X is not worse than Y in all other objectives. This is a fancy way of trying to say what we just looked at here intuitively, okay? Basically, it's talking about the boundary case. The boundary case being A and C, right? A is still dominating C because it beats C in at least one metric. And in the other metric, it's tied, so it doesn't beat me. Yeah?
What if you come into like an edge case where everything is equal? How do you make a decision?
Well, we're getting right there. It's not even necessarily that everything's equal. What if I have 100 options, but 15 are in that case of like, how do I pick? That's what you're getting at, right? If I just have a very large group of, if I have some subset, which might be the whole set, if I have some subset of options that fall on that boundary line, the example of like A and D, okay? If I have something like A, well, we can do E and F, or E and D, pardon me, because they are the dominating set. I have 1, 2, 3, 4, 5, but of those 5, I've got 2 where it's like, well, what do I do? It could be the case that I have 1,000 and then 100 of the like, what do I do? Yeah, okay. Pareto optimality is now where we're getting into what you're talking about. Raise your hand if you've ever heard of Pareto before. All right, cool. Good on you. He was like the stats guy. So let's say I've got these two things now, and I want to minimize both. And here are all my options, okay? There is a subset of those points that exists on that dominating boundary, on the Pareto front. We've got a bunch of examples that are dominating, or that are dominated by other things. But then there's a bunch of examples that are like, well, we got a decision to make. These points here dominate all other ones. Right? Because no other points, like the points up there, are just absolutely beaten by the points on the front in every metric. But those red points, that's where one of the metrics, we've got that conflict. The trick then is, okay, if I ran my evolution, I let it run for 1 billion generations and I got my population, here's what I could do, is I could take my whole population, effectively make this plot, And then go and be like, okay, I like that one, that one, that one, that one, that one. Those are all the good ones. And now you ask the question, well, how do I pick? That's what you're getting at. With this strategy, you don't. With this strategy, you don't have to pick one. You've got a set of options now that are all similarly good. Now, I have some subjective things I care about. Maybe I really hate walking. So I will pick the option that's closer. I know, sure, it was $50, but at the end of the day, I'm gonna pick that one because X, Y, Z. Or maybe at the end of the day, I come up with two where it's like, you know what, flip a coin. One of the awesome things about evolutionary computation when doing multi-objective problems is, by nature of it being a population-based search, you end up with a set of good solutions. All are going to be reasonably good. Some are going to be better than others, and some are going to be better than others in both metrics, and some are going to be only better than others in one metric or the other. But at the end of the day, you get a subset of them that are all good. And if I need to pick one of them to solve my problem, I have the luxury of choice. I now, as the human, get to decide, I like that one. Or I like those two, flip a coin. Does that make sense? So now you're in a position where you don't really need to make that choice. However, that's assuming we get to the end. There's a big gap in what I just explained. Well, when you are evaluating the fitness during evolution, how are you doing selection based on a fitness metric? Like, how are you calculating fitness? Because the Pareto strategy is almost like an alternative to the weighted sum. And you could do something like a weighted sum and at the very end do your Pareto front. Doesn't really matter. But what a lot of people will do is they will, or what's really popular when taking this Pareto strategy is your fitness functions, assuming you're minimizing both, your fitness function ends up being calculate who's in the dominating set. Give them a fitness of 1. Now remove the dominating set. Who's in that dominating set now? Who's left over? So for example, if I take this one out, this one out, this one out, and this one out, the dominating set then will become this one, and this one. So this has rank 2. And then rank 3 would be, I guess, this one here. And then rank 4 is this. So your selection is on what layer, like how many Pareto fronts back am I from the best? That's your fitness. That's how you do the selection. And of course, you can add that into maybe even a weighted thing. Maybe you still do the weighted thing, but then you also add the Pareto front rank as one of the metrics as well. You could do whatever the hell you want. Remember, this is evolutionary computation. Sky's the limit. Just see it. So there's one of the ways. There's another popular way of dealing with it. I'll tell you right now, the two most common ways of doing multi-objective is weighted sum and Pareto. When you only have 2 or 3 objectives, when you have a relatively small number of objectives, weighted sum is great. But as soon as you start to have a lot of objectives, weighted sum gets far too hard to manage. People find. Maybe you think it's easy, whatever. Pareto starts to get really great once you start to have a lot. Both are very common. 9 times out of 10, if you work on some research and you do weighted sum, you'll get some asshole going, why didn't you do Pareto? And then if you did it the other way, someone will say, why didn't you do weighted sum? Just because it's one of the, like you could pick one. It doesn't, they got pros and cons. Maybe you try both and you pick one because it just gave you better results. Whatever. Any questions about that? Cool. All right, so here's the plan.